Welcome to the fascinating world beneath our feet, where incredible geological processes create some of the most prized treasures on Earth. Gemstones. Specifically, we're going to delve into the science behind two beautiful varieties of the mineral beryl, the ocean-colored aquamarine and the lush green emerald. Understanding how these gems form, where they are found, and how we search for them is a journey through geology, chemistry, and cutting-edge technology. Geochemistry, the study of the chemical composition of the Earth's rocks, minerals, and fluids, plays an incredibly important part in this journey, being relevant to every stage of finding and extracting these valuable resources. Let's start with the mineral family tree. Aquamarine and emerald are both varieties of beryl, which is a beryllium-aluminum cyclosilicate with the ideal chemical formula aldeb, SeCos. Beryllium minerals are rock-forming constituents found in certain metamorphic, hydrothermal, and igneous environments. Beyond their beauty, beryllium minerals are important as are materials for beryllium. And beryl itself can be used as single crystal material for special optical purposes, like masers and lasers. Other beryllium minerals sometimes associated with gem deposits include bertrandite and phenakite, which are also mined as beryllium ores. Now let's talk about aquamarine. Imagine the serene colors of the ocean. That's the essence of this gemstone. Aquamarine gets its captivating blue to greenish-blue color, primarily from trace amounts of iron within its crystal structure. Geologically, aquamarine is often found as gemmy crystals in veins within granite pegmatites. These are late-stage, coarse-grained igneous rocks formed from the final crystallization of granitic magma. Hydrothermal processes also play a key role where hot, mineral-rich fluids move through cracks and cavities in rocks, depositing minerals as they cool. Aquamarine can crystallize in these hydrothermal settings, particularly those associated with granitic rocks. It can also be found in secondary placer deposits, which are formed when the original host rock erodes. And the resistant aquamarine crystals are washed downstream and concentrated in riverbeds or alluvial fans. Some major geological locations where aquamarine forms include Brazil and Pakistan. Emerald, the king of green gems, is a bit more geologically demanding. Its vibrant green hue comes from trace amounts of chromium and or vanadium replacing aluminum in the beryl structure. Unlike aquamarine, emerald formation often requires a complex interaction between beryllium-rich fluids and chromium or vanadium-rich rocks. Think of it as a geological party where two guests who normally wouldn't meet have to get together to create something spectacular. There are two main geological types of natural emerald deposits. The first type, often called schist-type deposits, is associated with pegmatites or granitic dikes and hydrothermal veins that cut through mafic-ultramafic or sedimentary rocks. Many deposits worldwide, including some in Brazil, Africa, India, Australia, and Europe, fit this description. Here, the beryllium source is typically the granitic pegmatite, and the chromium-vanadium comes from the surrounding mafic-ultramafic or sedimentary rocks. Fluids circulating through these pre-existing rocks cause metasomatism, altering the rock chemistry and allowing emerald to crystallize. Sometimes, these pegmatites might even become desilicated due to the hydrothermal fluid interaction, forming rocks like mycoplagioclase or phlogopite rims and vinelets. The second main type of emerald deposit is linked to tectonic activity, such as thrusts, faults, and shear zones, and is often disconnected from obvious pegmatite sources. These deposits occur in chromium and vanadium-bearing rocks. The most famous examples are the world-leading emerald deposits in Colombia. These are unusual because there is no evidence for nearby magmatic activity providing the beryllium directly. Instead, the emeralds formed from hydrothermal growth related to tectonic activity. Studies suggest the parent fluids were highly saline brines, potentially formed at depth from meteoric and formational water. Interacting with salt beds and evaporitic sequences interbedded with black shales, these fluids buried deep enough to reach significant temperatures, migrated upwards along tectonic structures, interacting with the black shales. During this interaction, trace elements like beryllium, chromium, and vanadium were leached from the shale and precipitated in veins and cavities, forming emerald along with other minerals like calcite, pyrite, and quartz. The Santa Terezinha deposit in Brazil is another example where a metamorphic origin for the beryllium-bearing fluids is proposed. As local magmatic sources or low B concentrations in the surrounding rocks seem unlikely, the formation conditions for emerald can vary. For example, studies on fluid inclusions in emeralds from different locations show variations in minimum trapping temperatures, ranging from around 240 degrees Celsius in some Zambian deposits to 400–450 degrees Celsius in parts of Nigeria and Pakistan, and even higher, up to 630–710 degrees Celsius in some Madagascar occurrences, along with high pressures. The isotopic composition of water trapped within emerald crystals can act like a geological fingerprint, helping scientists understand the source of the fluids involved in their formation, whether they were primarily magmatic waters, metamorphic waters, formation waters, or even from sediments. This isotopic data can also be used to distinguish natural emeralds from synthetic ones, which are typically created through flux fusion or hydrothermal processes. Finding these elusive treasures is where exploration techniques come into play. As gemstones become harder to find near the surface, technology is becoming increasingly vital. Geophysical methods, which use the physical properties of rocks and minerals to image the subsurface, are being applied at various scales. On a megascale, techniques like teleseismic signals, regional electromagnetics, and long-range seismic soundings can help delineate large, thick, rigid areas of the Earth's crust and upper mantle, known as cratons, and understand their internal structure. This is particularly relevant for searching for gems like diamonds, which form deep within the mantle keel of cratons. However, understanding regional crustal architecture can also provide clues for other gem types. On a mesoscale, techniques like electromagnetics, aeromagnetics, reflection, seismology, and low-frequency ground-penetrating radar can map individual geological features. These might include the granitic plutons or pegmatite dikes that host aquamarine in some emeralds, or the mafic-ultramafic bodies and shear zones associated with other emerald deposits. For instance, potential field data like gravity and magnetics can help delineate some mafic rocks. Moving to the microscale, high-frequency ground-penetrating radar and potentially even ultra-high-frequency seismology are being explored for their ability to identify smaller features. GPR, for example, has been successfully used to delineate gem-bearing cavities, sometimes called pockets, in pegmatite dikes. In one notable case, GPR helped find over 25 gem-bearing pockets in a Southern California tourmaline mine. After initial tests, successfully located a known pocket. The signals from GPR respond strongly to cracks and cavities in crystalline rock, offering a way to see potential gem locations underground. There's even hope that future advancements in ultra-higher resolution seismic methods might eventually allow imaging of individual crystals. Geochemistry is another crucial tool in exploration. It's analyzing the chemical composition of rocks, soils, and water can help identify areas enriched in elements associated with gemstones. For Beryl varieties like aquamarine and emerald, this means looking for elevated levels of beryllium. For emerald, the presence of chromium and/or vanadium is also key. Portable XRF analyzers are a modern solution for geochemistry analysis in the mining industry. These devices use X-rays to irradiate a sample, causing its atoms to emit fluorescent X-rays with characteristic energies and intensities depending on the element. A spectrometer detects and measures these emitted X-rays, allowing for the non-invasive identification and measurement of elemental composition. Portable XRF is incredibly important because it provides fast and accurate data, avoiding costly delays in exploration and throughout a mine's life cycle. It's making mines more profitable by enabling quick decisions based on real-time chemical data. Beyond specific elemental analysis, geochemists also look for indicator minerals that commonly occur alongside gemstones. For certain types of emerald deposits, minerals like chrysoberyl and phenakite can serve as obvious indicator minerals, signaling the potential for emerald mineralization nearby. Exploring for emeralds might involve plotting potential sources of beryllium and chromium, vanadium, and focusing exploration efforts where these potential reservoirs come together. Geochemical features like the ratio of certain elements can also help pinpoint highly fractionated igneous rocks more likely to host gem-quality beryl. Mining itself, especially for small-scale operations, as sometimes seen with gems, involves practical considerations to manage risks. While the sources specifically mention advice for opal miners, Some points about safety in underground mining are generally applicable: establishing a mine plan, ensuring minimum depth to the roof of drives, maintaining adequate width and height for access, considering ground support for wider excavations, and having a second means of egress are basic safety principles. Underground mining also requires bringing in essential equipment, like suitable lighting fans for ventilation to ensure air circulation and remove potentially hazardous atmospheres, potable water, and basic first aid supplies. Checking equipment daily, inspecting the underground workings for changes, as cracks or fallen rocks, and wearing appropriate dust masks, especially when breaking silica-bearing rock, are important for safety. On the surface, securing shafts and voids when mining is finished is crucial for the safety of people, livestock, and wildlife. So, from the initial geological whispers deep within the Earth's crust to the high-tech search and careful extraction. The journey of an aquamarine or emerald is a testament to the complex and dynamic nature of our planet. It involves understanding ancient fluid pathways, atomic arrangements, and leveraging modern technology to uncover the beauty hidden within the rock. It's like a giant, very slow treasure hunt. But the prizes are stunning crystals formed over millions of years.
Welcome to the world of geology and earth sciences with Ricardo Valls, a seasoned professional geologist bringing you over 1,500 videos of unparalleled expertise. Whether you're a budding graduate student, an early career specialist, or a seasoned professional, this channel is your gateway to a wealth of knowledge. Explore a vast array of Earth-related subjects, including geology, geochemistry, structural geology, and the application of artificial intelligence and machine learning in geosciences. Ricardo Valls not only shares his own invaluable insights, but also brings you exclusive interviews and collaborations with other prominent geologists, offering a comprehensive view of the field. Stay ahead of the curve with our latest content, covering everything from unraveling the Earth's secrets to exploring global geological phenomena. Don't miss this opportunity to enhance your knowledge and stay at the forefront of the industry. Subscribe now, hit that like button, and share this invaluable resource with your colleagues and friends. Join our growing community of over 2,000 earth science enthusiasts and professionals today. Unlock the secrets of the Earth with Ricardo Valls, your top resource for all things geology. The future of geosciences is here. Be part of it.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.